So we're going to just continue. So in the last, at the end part of the class, we're basically seeing the limitations of two in a cross section, how the causal supplementation of observable data, but by interpolation of unobserved values means. Quantum mechanics, when constructed, they do not admit a causal supplementation of interpolation. So you cannot go back and pin down those conjugate variables whose effect can be traced to different causes. But in today's class, what we are going to do is we are going to have we are going to have some sort of graphical or pictorial way of trying to visualize these variables in that sense. So, in terms of some probability distributions, so which we study in normal quantum mechanical classes, how we see it. But here we have its analysis in terms of these variables. So the question is that of the probability distribution. So if we consider the fact that P and Q cannot be exactly determined, so those conjugate variables, so if we take them, if we represent them in terms of P and Q and in normal, so we can identify P and Q with position and momentum if we identify them. But the identification is in the classical mechanics, the identification is P and Q, these, so you can, we say they commute in classical language. Means we can simultaneously identify these two variables in terms of measurement without any discrepancy. But in quantum mechanics, there is, so if we just, before coming to quantum mechanics, if we say that P and Q, it's not a matter of determining, it's a matter of exactly determining things. So there is, the measurement is not, you cannot in principle, what I should say, improve upon our measurements. In classical things, you cannot still that probability distribution is there in classical statistical mechanics, but in principle we can improve that measurement to an accuracy, to an infinite accuracy. So if P and Q cannot in quantum mechanical language or in that diction cannot be exactly determined, then we must replace these P and Q as probability. We can replace these strict statements. These statements can hold in classical formalization of things, but these strict statements have to be replaced by probability statements. The word probability here will it will uncover that discrepancy can be taken care, at least conceptually, when we talk of probability in that sense. But the probability, yes, that's it. In which to every coordinate q, every coordinate q, and to every p, value of probability will occur. So symbols. So you can have these symbols can have that the way we have probability can have probability. These can have meanings in terms of distributions where the probability spread can be, or the values can take certain values from ensemble of values. It can fluctuate, or it can the value can range from certain set of values to certain set of values where this probability distribution may lie. So the expressions can be denoted as dp and dq, which might be correspond to different mathematical functions. And in small interval, you can say it dq dq or dp dp. So we're identifying these conjugate variables whose measurement is not precise in the way we do it in the classical sense. So the range of these probability densities may range from q1, q2, dq, dq, and for this momentum it might be p1, p2, d pi, dp, dp, where q varies from q1 to q2 and p varies from p1 to p2. So probability measurements are basically meant to be a set of measurements and not individual measurements. That's it. Because that's not, they are not, so in mathematics we study normally the Gaussian curve is basically studied in that context. It's a sort of bell-shaped curve, and if we just want to just have a representation of that bell-shaped curve in terms of these two curves P and Q, so one can be like this, and one can be like this. It might be steeper, and other can be like this. So this is 2, this is 2, this is 1. So it's, you have to see it's Q dq. It's how these curves will just how can pictorially see how they under these conjugate parameters how they will evolve. Basically, it's basically psi as a wave function or a complex wave, which has some identification with the real wave, how it evolves in space and time, and vis-a-vis these conjugate variables, position and momentum, or energy and time also sometimes. So the more important point is that we have constructed them in terms of cross-sectional variables. That statement of cross sections, where we assumed that in cross-sectional analysis we assumed that we used the word cross-section. The laws directly connect simultaneous value of physical quantity without being reducible to the effects of common causes. So the effects are not necessarily reduced to the common causes. So they are different causes can lead to different effects, and those effects can, whether they can be measurable or not in the exact sense. In the classical mechanics we can measure them in the exact sense, in the quantum mechanics we cannot. So if it's a bell-shaped sort of curve, where if you want to maintain a logical connection, so there's the mathematical principle which determines these both curves, dq and dp. So one of them is, so you can have these two curves, dq and dp, at a given time, at a given time. And derivable from, so we have a derivable from the mathematical function psi of q. So this psi has a certain connection with p as well as q. So this psi is a conjugate function of p and q. Or the psi has the shape of psi has some logical connections with how p and q evolve as conjugate variables. So this, which means that if one of them is steep, the curve is steep, the other will be rather flat. If it's steep, the other will be flat. So if other will be come closer, it will be flat. If it will be steep, the other one will be flat. Such that physically it means that measurement of exact measurement of p, exact measurement of p will make q imprecise and vice versa. Exact measurement of q will make p imprecise. That's it. The more we concentrate, so it's sort of that complementarity principle. If you concentrate on one variable, the other becomes, the measurement of other becomes less exact. Or if you measure, so they have sort of inverse relationship. And historically, you can say it the way this de Broglie and Schrödinger, they took analogy from how we just try to imagine Huygens wave theory in wave optics. So you can see its roots also there, this interpretation of psi function, psi square. Now the point is, so the shapes of these psi k and psi p, so they have an inverse relation. So normally it's psi of maybe qt. So the wave function psi, its dependence upon this dpt and dqt. So we normally will just ignore time as an independent variable. So rules for the square function psi. Rules for the square function psi are that since it's a complex wave, we say that the psi, so the way we have intensity, in the same way we have psi of q square. It will give us the so you can have it's the way this you can have this thing that the way we have a normal wave understanding of waves, how two or more waves superpose, and different waves, the superpositions, they might have different overtones or harmonics, where the superposition is maximum or minimum. That's it. So how we, basically the identification of momentum in terms of, since it's a complex wave, but wave has sort of wave spread. And how can conceptually or pictorially identify wave in terms of particle? P is equal to h by lambda. Momentum and so where this how do we identify this wave? So we will not say it's a wave, it's a wave packet. There are series of waves, they continuously interfere, and in a certain range where they will interfere maximum. So the amplitudes will be maximum. So that will be inversely. So we'll say the wave, the spread will be where the wave will be maximum, wavelength will be maximum, momentum will be minimum. Where the superposition will be maximum interference, and it will concentrate at one point. So we'll say the momentum is maximum. So where wave spread is maximum along a long distance, the momentum is the minimum, and vice versa. Where the momentum is maximum, where the wave spread is concentrated in a wave packet, so we'll say we identify the momentum at that point of that thing. And it's now also called in this sense. It's also called something called. These are is a rule of spectral decomposition, which says that the probability of observing a value p is determined by the amplitude sigma lambda within a spectral decomposition such that dp is so 1 by x, so it will be constant. You can see it is sigma lambda square. So psi basically psi establishes the relation between two distributions. The distributions may be dp and dq. So the way we have identified, ultimately we have to identify psi in terms of this psi square. But psi is dependent upon this distribution and this momentum. But this is in turn, we say that we have identified this sigma as the amplitude. So amplitude is maximum, where amplitude is maximum, that's it. Or we also have related with it, we have identified psi with amplitude and it with momentum. So where the momentum is maximum, that's it. The amplitude is maximum, so we identify P with sigma, and we can say this can hold, this relation will hold. Now, if we want to have, for example, how we can have this principle of indeterminacy, that we cannot determine things. Where does this come? So again, if you want to pictorially see, you can see it pictorially in the sense that if we want to maintain, so the previous graph we did not show it individually. If one is made steeper, the other becomes flat. If other becomes, you concentrate on one, the other becomes imprecise. So it can be better explained by these two graphs. Like if it's one way it goes in one direction, another goes in this momentum variable in this direction. So it's P, and it's Q. So it's delta Q. So if you want to make it more precise, so it will become like this. So in the process, when you make this more precise, it will just spread out. If you become more, if you concentrate on this closer, so they will have these two things will have some inverse, these graphs will have some inverse relationship. If you make one more this closer, and the other will spread out respectively. Such that if D, P, Q and D are two distributions. So these distributions basically are these wave packets which are evolving. So in a certain range or frequencies where they are superposing. And psi is dependent upon P and Q. So exact identification of psi in terms of these two variables leads to sort of indeterminacy. That's it. And that's exemplified is called Gauss's curve, we know it. Now the important point is that so where is the problem? So problem is that physically, if you want to, why should we? For example, if we want to make a physical identification with that of a waves which are continuously propagating, waves of different frequencies, and we normally use Fourier analysis in that thing. So waves ascender or so they will have different waves, will have different frequencies, will have different amplitudes. So it's only in certain range of frequencies which will correspond to those probability distributions, those range of frequencies which will interfere in a certain way and in that wave packet which will correspond to this thing, that where a wave packet will be maximum, that maximum will come out and we can identify that maximum with some momentum. So it will not occur in some general sense. So the evolution of wave spread in terms of wave packets in space, it will have that wave packet or wave spread will be between a certain different frequencies above and below a certain range. Above that range it may not occur, below that range it may start to occur. So there may be a certain range where that wave packet can be observable, which will correspond to the psi, which has a direct conjugate dependence on Q and P. So that's it. Or inverse correlation of, if the word is there, inverse correlation of harmonic analysis corresponding to these wave particle phenomena. So if I use the words of this sentence, so the principle of inverse correlation means that it's impossible to identify impossible to, rather not identify, not a better word, it's impossible to unify fidelity and high selectivity in the same adjustment of the observer. This is what I was saying, same adjustment of the. So if that wave packet will only lie in that range, the observer who is going to observe it, so he has to have interface with that thing. those waves spread. So how can he observe those range of frequencies? So it's a sort of this thing that fidelity means you cannot have that purity of observing those things with the high selectivity. The way we want to select in which range those frequencies should be there. We have to also use our observables that will disturb that system, that wave packet. So, selecting a certain range of frequencies and observing them in the purest form, it's an experimental limitation. But you can say, you can identify the conceptual limitations of identifying psi in terms of variables q and p, which are conjugate in their determination, estimation, or observation, you can say. Now, you can, so here one thing is that so you can say of law of inverse correlation of the probability distribution between momentum and position, sort of. So it can be seen as a law, inverse law. If one is identified, position is identified, the momentum becomes imprecise in that conjugate sense. So it's an inverse correlation of law of inverse correlation of probability distributions. If those wave packets are identified with some probability distributions and two parameters are chosen, position and momentum, in the sense that position is that exactness in that wave packet, where wave packet is, and the momentum which is identified by this lambda being this p, so that comes in some inverse form. So we can say that the difference between, so we can take this to the identification of kinematic and dynamic variables, if we can, and see them in terms of inverse correlation. Kinematic means you identify with the causes of the forces and not the motion itself. In the later we can have motion itself. So you can identify this kinematic and dynamic factors. So this thing has this whatever this discussion we are having. So we can say that this is basically the way we or Heisenberg, we just see in the books, or Heisenberg identified it. So if the curve exists between q minus, I said it, q minus delta q and q plus, in that range in which those frequencies can be audible or observable or perceptible, that wave packet below a certain range and above a certain range. So you can say q minus delta q, which will correspond to that probability spread, identified as probability spread, if this variable is seen in that way. Or in the same way you can see momentum also, this p minus delta q and this p plus delta q. So, and you can see in terms of Gauss curve, so you can say that delta p into delta q, this is the way we see in books, or if we identify p and q in terms of psi, so it's greater than h over 4 pi. So we have not identified other, you can not only identify position and momentum, you can also identify time and energy. So you can have, if you want to see the energy of the thing and the time, you cannot, you can have this inverse correlation or this also exists in terms of probability distribution. If you see the spread wave tide, you cannot determine entirely the energy as well as delta t. In that, it will also come in that inverse relation. Now what? So if I just say Heisenberg expresses the relationship of measurement, of position and momentum by saying that if you use the words language of statistics, that standard deviation in Q implies a small standard deviation in Q implies a great standard deviation in P, and vice versa. So standard deviation, you can see in small. So if we have a small standard deviation in P, it will vice versa. If it's in this thing, so you can have how you just see standard deviation, how you see variance, how you calculate that variance. So if you have P and Q as two conjugate variables, and we just want to have a standard deviation of one vis-a-vis other, and basically in our case this is basically the probability spread you are measuring vis-a-vis these two parameters. And in classical case, PQ minus QP ought to be 0. H will be equal to 0. So now I will come to the very end, which will justify our this thing. The philosophy. What is the what? How can we? What do we get out of it? If two conjugate variables cannot be measured in precise, in some precise sense, the way we measure in classical sense. So what will it say? So does it question the legitimacy of quantum mechanics as a precise or as an exact science, the way we define science in the sense it's observation, experimentation and prediction in some quantitative or in some precise sense? Does it question that? Or rather we can say that physicists should maintain some fundamental theorems, and he is entitled to limitations of predictivity or predictability is the proper word. So we can in that the way we define science in that precise sense, in that Laplacian sense, give me initial conditions, I will know where the universe will exist, wherever million years. So that the hallmark of science. So does it question is it questionable in that quantum mechanical sense or not? Or physicists should within that domain he should retain that within the limitations of predictivity he can do science. So it's a no problem. And even there can be statements, we can have mathematical proofs to quantify these statements, the way we do in terms of uncertainty relationships, Heisenberg's conjugate relationships. We can quantify them as some part of mathematical statements structure. So, here comes the point of Reichenbach. So, here comes the philosophy of part of the quantum mechanics. So, what does it all mean or implicate? So, this means for Reichenbach, what he says, the principle of indeterminacy is an empirical statement. So, what Reichenbach wants to say, that the way we have the empiricism, he wants to say it's cut and dried, it's a consensus which cannot be somehow questioned. But the point is that you can make sense of this statement in some larger sense of scientific determinism. That we have the advent of quantum mechanics. If we cannot measure some simultaneous measurements in precise sense, it will question our predictability about a given system. Or in that sense, it will question, in some sense, our notions of scientific determinism. But so there can be two opinions. The opinion of one of the opinions, strong opinion of which is followed, is that still we can say we are talking of imprecision it's still an empirical statement, in the sense that we can predict nature, but we may not predict it in some exact sense. So it has nothing. So this is the point, you can say. So if I use if we use a psi function, the relations of, or rather we can say that in quantum mechanics, which is considered as a statistical part of science, is embedded in the universal science of causal character. So you can also, if you cannot determine things, does it also say something, since relations of quantum mechanics should be embedded in the universal science of causal character. Causal, it's not only scientific determinism, it's also sort of causal determinism. Becomes some sort of suspect in that sense, that we describe a variable in space-time. If you cannot have that causal intuition, somewhat in that exact sense, or in that precise sense, so what does it say? So it opens a lot of can of worms, whether the predictivity and prediction. One is prediction. Another is the post-diction. So in post-diction, you can see retrospectively. You can look your present or future from the past. So that sense, that thing is somewhat compromised in that when you cannot make the simultaneous or precise measurements of two variables, two conjugate variables, which may be traced to some different causes. That's why we used statements of cross-section to begin with. So if it is that way, what does it speak of predictability? So here I'll make some. Since Reichenbach is converted to the philosophy of materialism, philosophy of empiricism, so so it's a huge debate that materialistic metaphysics or scientific empiricism. So if we cannot, the causal determinism cannot be that rigid or cannot be held that sacrosanct. Should we do away with the doctrine of scientific empiricism in that strict sense, or the metaphysics associated with empiricism as a philosophy, or determinism as a philosophy, or human mind, capacity of human mind to determine things to the utmost accuracy. That you can take it either, if you want to cultivate it that way, and mathematically you also quantify those indeterminacies. Your system is a defined system, or you axiomatize or formalize mathematically, and a system with these limitations, it's fine, there's no problem in it. You can say nature is like that. But you can also question the other sacrosanct values of determinism, scientific determinism, causal determinism associated with quantum mechanics, and which might have some other features. There may be other things, other interpretations where causality may not be strict. There can be vertical causality also. The notions of prediction and post-diction, the future and past, how we can, the notion of time, teleology of time, how we can see it. Do events always have to be seen in a certain way with a certain teleology? So these are different discussions. So I'll here stop saying that you can, as an working physicist, you can still believe in, as a philosophy of science, you can say that empiricism as a construct can be somehow adjusted to this thing, but it also can be interpreted in a. You can have other interpretations also, viable. One should be open to other viable, other interpretations also. So I'll stop here.